All right, welcome to the after work video, and I have monitoring enabled, so I will turn that off. There we go. So that's a lot easier. Um, uh, there. Now I can talk. I don't hear my own voice, but that makes it easier for me. Okay, so we're going to keep going. We just finished talking about clustering. So, like, how do you identify clusters in the data? That matters a lot because you can see that there's problems if you don't, or you get a lot of different results. We also talked about uh, ways of rescaling the data, normalization, standardization. Uh, those are the two ways we talked about when it comes to uh, data rescaling. And when it came to clustering, we talked about centroid based clustering, and we also talked about and that's the only clustering we got to so far. So we're going to learn about another kind of clustering, density-based clustering, but we're still learning about centroid-based clustering. The idea is the following. The intuition of this clustering method is that if you have the correct number of clusters, the centroid will likely be positioned at the center of a set of observations that constitute such clusters, and therefore all of them will be significantly close. Suppose the number of clusters is lower than optimal. In that case, the centroids will tend to be, on average, further away from many observations. On the other hand, if the number of clusters is too large, you can expect observations to be much closer to centroids. In the limit, if you set the number of clusters to be the same as the number of observations, the distance to the centroids will be zero. So a metric called within cluster sum of squared errors, WSS, can be computed for a particular set of clusters. If we cluster our data set for different values of k, let's remember, most of the time we will not know what the suitable k is. The shape of the curve of WSS based on k will be like the following. So it'll be shoot. This is what I love about ChatGPT. Okay, so ChatGPT, and we're gonna ask it a few things. The first thing we're gonna ask it is to describe this mathematical shape. So I'll paste in the screenshot, and I'll ask the question: describe this mathematical shape. Tell me the mathematical terms. Explain the mathematical terms. Relevant to the shape. Then zoom out and explain more mathematical terms within this category of mathematics to help improve my mathematical intuition. Oh, yeah, it's an elbow curve. But like what's the Yeah. Well, that's cool that it that's awesome that it knew what it was. Cool. That's cool. What category is this in? Yeah. Which optimization subcategory does this fall into? Combinatorial. It's discrete. Solution space is discrete. Okay. I think I had one more question. So like I guess what I was thinking is more like the curve of the graph. Like I was thinking you're like x squared or like the logarithm of x, like like a linear graph. So like in that regard, like logarithm or like x squared, like how would you describe the graph in that way? Like in a more simply mathematical term. Yeah. Yeah, the function. Yeah, yeah, yeah. It's a log. That's what I was thinking. All right, like is it useful to think that way, or is that a poor mathematical intuition? Oh, that's good. Okay, good. Well, help me build out that intuition. Good, good, good. Okay, well, that's good to hear that it is a good intuition. Can you help me make this intuition better? I guess kind of what I was thinking of was that it was a logarithmic function. But the thing is, like, a logarithmic function, I guess I would think would, instead of starting with a deep decline that flattens out, it starts with a steep increase that flattens out. But like those are both logarithmic functions, right? It's just one is negative and one is positive. And a log is just right. Okay. Is there like a tool for that? Ugh. Is there like an online tool or some free service that I can use to do that practice? Which one? Brilliant? I want a Brilliant sponsor. I'm like desperate for a Brilliant sponsor on this channel. I'll do anything. That sounds good. Oh, this is cool. I like this. Oh, I like this one better. Cause I like this one better because it's all out there. Yeah, and then you can move it around. You can put a point on it. I like this one a lot better. You know what? I think I'm gonna, cause in my hobbies, one of my favorite hobbies is information. So I'm gonna make a new folder in that and call it mathematical tools. Cause I just want to be the kind of person that bookmarks mathematical tools. All right. This is the one I've heard of. This is kind of like the popular one. Mathematica is like, but what I like is things that are like really easy usable. So like, yeah, I already this is already more complicated than I would like it to be. Like what I liked about this one is like you click on it, you click start calculator, and it like it looks like a regular calculator. It's just a graphing calculator. It's like you can graph a function. So let's graph the cosine of 1. Oh. Wait, how do I draw it? How do I draw a graph? I'm on a huge tangent here, but how can I use this tool? How can I use this tool to draw A circle. I'll go through the other ones. Graph.tk, that looks like a good one. Oh yeah, I like this one's pretty good. See, this one's hard to use. Oh, there we go. I really like this one. And then you can delete them. Yeah, cool. I don't know what this means. I really like this one. But I wasn't able to draw a circle. So click on the input bar on the bottom where it says input, which I don't see. Oh, here we go. I see it. Draw a circle with center at the origin, radius 1. You would input this. So let's do that. Oh, you know what? It gets messed up. The exponents get screwed up. There we go. I was like, that doesn't look like a circle. Have I not been studying math for that long? Forgot what a circle looked like. There we go. Now we've got a unit circle. So yeah, so okay, remind me of all the essential things to know about a unit circle. Yeah. Yes. This is a unit circle. Yes. Oh, right. Okay. Yeah. Right. Right. Yeah. Right. Oh. I want to see it in. Well, shoot. I want to see it with like. Well. Anyway, I'm off on a tangent here, quite literally. So let's get back to the book. we can intuitively identify how the gains in WSS accelerate as we go from k equals 1 to k equals 3, but from then on they stagnate. There is still an improvement, but very small. The k value that represents the elbow of the curve, so that's this one here, is identified as the optimal. In our example, k equals 3. However, as referred to, the only way to know is by running k-means multiple times. Brute force is your friend. Density based. In this type of clustering, observations are clustered together based on density. Usually, a sensitivity parameter is defined to determine the minimum density required to consider a particular observation in a cluster or otherwise be considered an outlier. dbScan is a popular example of a clustering algorithm of this type. Okay, so there are, in addition to the other kinds of clustering, to the first kind of clustering algorithm we talked about, which is a centroid-based clustering algorithm, and I'll go and confirm that because there's a lot coming in here and I don't want to get it wrong. Yeah, so there's a centroid-based clustering algorithm of types, and one example of a centroid-based clustering algorithm is the k-means centroid-based clustering algorithm. But now that we're moving on to density-based clustering algorithms as opposed to centroid-based, we're going to learn about the dbScan example of a clustering algorithm of the type that is density based. Because dbScan is not dependent on the distance to a centroid, it can capture more complex shapes of clusters in the n-dimensional space in the data. In an algorithm like dbScan, we need to specify parameters to control the sensitivity of the algorithm in particular. In an algorithm like dbScan, we need to specify parameters to control the algorithm's sensitivity. In particular, so this is a parameter that we need to control in the dbScan density-based clustering algorithm. So the first one we need to control is epsilon. It determines the distance required between two observations to consider them part of the same cluster. It represents the radius of a circle drawn around each observation. Any other observation within that circle will be considered part of the same cluster. It is a measure of the density of that area. So the next parameter that we need to specify to control the dbScan sensitivity, and remember dbScan is a clustering algorithm that is density based, is min PTS. Minimum number of points that should exist within the epsilon radius, the e radius circle around it, and it's not e radius, it's epsilon radius. Yeah. E radius circle around it to consider this observation a core point. If an observation has no other one within its epsilon radius circle around it, it will be considered an outlier. And I want to ask, how bad of me would it be to call this an E radius rather than an epsilon radius? Yeah, it's not the letter E, it's the letter epsilon. But isn't... Yeah. E is already used. Right. Oh, really? Yeah. Damn it. Yeah. My brain's doing that thing where words like my brain is doing that thing where like I honestly thought neighborhood was spelled like that. All right. Well, I've got a few more minutes here. This is a lot. This is a lot. But okay, let's continue. If an observation has no other one within its epsilon radius circle around it, it will be considered an outlier. DBSCAN has the advantage of being able to capture more complex shapes of clusters and is adequate when your dataset has outliers, but on the other hand, it is susceptible to the parameters we choose. A similar mechanism to the elbow method exists to identify the optimal epsilon value. Hierarchical clustering. In this type of clustering, it will progressively evaluate all the observations, compute their distances, and hierarchically create clusters. Okay, so we've got more types of clustering. The next one is hierarchical, whose distances will be subsequently computed, and clusters of clusters will be created, and so on. An excellent example of hierarchical clustering with a bottom-up approach is the hierarchical agglomerative clustering. While these algorithms work well, they are pretty resource intensive and do not scale well when the number of observations is vast. They may be an excellent choice to have a first idea of how many clusters your dataset may have. Say you pick 500 observations and apply agglomerative clustering. With it, you may have a first view of how many clusters your dataset has. With that target number, you can use it as K. For example, in K-means, to perform a larger scale clustering. And remember what K-means is. K-means is a algorithm that is used for centroid-based clustering. Oh, I feel like I had to cheat and look back a little bit, but I feel like I got that right. So K-means is an algorithm that's used for centroid-based clustering. And we can use with that target number, you can use it as K, for example, in K-means to perform larger scale clustering. All right, so here we can see a hierarchical clustering dendrogram. So we've got something quite complicated there. Let's feed that into ChatGPT, and we'll put the key takeaway in there as well. Huh. Oh, yeah. There's a really cool dendrogram. I thought it was called the Tree of Life. Uh, yeah, it's like this, but it's cooler. Yeah, onezoom.org. I think this is it. Yeah, this is what I was thinking of. Yeah, no, this is it. So this is a dendrogram, right? A dendrogram is a diagram representing a tree. Yeah, so this is a dendrogram. Yeah, so let's see where oak trees are. Oak trees are there. Very nice. Okay. Oh, watermelons are on the same branch. Or they branched off. Oh. Anyway, this is interesting, but it is outside the scope of this series. So the key takeaway is with clustering algorithms, we will always need to guide the algorithm to discover the right clusters or right number of clusters. There is no one size fits all. All right, next section is anomaly detection. Anomaly detection is a very broad term, but includes all the different techniques intended to identify which observations in a sample do not fit. There could be various types of use cases. Number one, there is a time series and the values at certain points in time are abnormally high or low compared with what is normal in that sequence. This is time-based anomaly detection. For example, there is a large peak in traffic in a time series of traffic on an interface in a router. Whatever, that's fine. Such a large peak may be anomalous, and we may want to know more about it. This is a use case for anomaly detection to identify traffic spikes. There is a set of observations from a number of entities for a particular metric, which due to their nature, you might expect them to have similar values, but one or a few of them are far out compared to the rest. They are outliers. One example is, going back to our top of rack switches, if we have 500 of them across various data centers, you may expect maybe that their memory consumption will be in the same range, whatever it is. Let's say it ranges between 20 to 25%. But 3 of those switches have a memory consumption in the range of 50%. While 50% utilization does not seem harmful yet, the fact that these 3 have such a difference compared to the other 497 is probably something you may want to know about. Therefore, there are outlier detection techniques designed for that purpose. And I don't have forever, so I'm looking for a stopping point here. There isn't one coming up, so I think I will stop pretty soon here. I'll stop here at the break there. There is a set of entities you are tracking. Let's say again, top of rack switches. You are monitoring a set of input variables for them, such as number of ports utilized, number of VLANs, number of VRFs configured, number of routes, number of filters. At the same time, you are monitoring its operational state. For example, memory utilization. Memory may vary across the devices because the input variables that drive the memory utilization may also change. There is a certain relationship between the input and output variables. We may or may not know it. Normal behavior is determined by such relationships. But due to different circumstances, let's say a configuration change or a software change on the switch, such a relationship may change and become anomalous. Therefore, sometimes the anomaly may not only be about the value of the metric itself, memory in this case, but about the relationship between a set of entry variables and an output metric. There are different techniques to detect anomalies or outliers. I will briefly describe a few of them in this section, and more details will follow in the practical cases later in the book. And I will stop it right there. I just wanted to do a quick video. So get rid of all these bookmarks. I have to keep doing bookmark after bookmark because it's just so dense. I don't want to have to lose my place and go back because that would just completely break my line of thinking with this. It's it's pretty complicated stuff, and he actually says no, it's not. It's a basic to intermediate level, which I definitely can believe. Math ever goes onward. So but you know, this is the here and now. We've got ChatGPT. So as I've said before, the first wave of the AI revolution for humanity is personal tutoring. So that's what I've got here. I've got ChatGPT 4, pay $20 a month, and I'm using it as a personal tutor as I read this book to kind of remind me of these math concepts. And I guess I'm a ChatGPT salesman because I guess this is now an ad for ChatGPT. So yeah,